In figure 842, we have this block sliding down the spring. The incline is going to compress this spring about 0.21 centimeters. So I'll read the problem now. A block of mass 3.2 kilograms slide from rest a distance d down a frictionless incline at an angle theta of 30 degrees, where it runs into a spring constant 431 Newton meters. When the block momentarily stopped, it has compressed the spring 21 centimeters. What are the distance d and b, the distance between the point of the first block spring contact and the point where the block speed is greatest? So we'll first calculate the total energy in the spring once the block has completely compressed the spring to 21 centimeters or 0.21 meters. So potential energy in the spring is equal to 1/2 kx squared, which is just going to be 1/2 times 431 Newton meters times 0.21 meters squared, and that's going to equal 9.50 joules. Okay, we're going to draw our own sketch and sort of look at what's going on here. We have an incline. We have this spring. And we have this block. And it has a 30 degrees. And we know all our energy is going to come from this height portion, because it's all gravitational. We know also when it hits the spring and compresses the spring, it's going to compress the spring down to where it has a potential energy of 9.50 joules. Now, question B wants to know, what is the distance the block slides, the total distance it slides, plus the compression? So first, let's figure out H, and we'll just call the slope of the incline L. So the sine of theta is equal to H or Y, whatever you want to put in, over L. And that goes to H is equal to the sine of theta times L. So we know that H is sine of theta times L. The force this block going down the incline is mg sine theta. Now, if we multiply that by L, we'll have the total amount of work this block performs sliding down the incline. That the distance it slide plus the compression of the spring. And we know what W is. W is 9.50 joules. So let's make a little bit more sense out of this. This is going to go to mg sine theta. Now L is two parts. It's the distance it slides, which we don't know, plus the compression of the spring that we do know, and we just set it equal to what work is, which is 9 equals 9.50 joules. And we can solve for D. When we solve for D, when you solve this equation for D, you get 0.39 meters. Part B, the distance between the point of the first block spring contact and the point where the block speed is greatest. Okay, for part B, we have minus kx. And I'm just doing this. That's the force of the spring. Must be equal to mg sine theta. Now, when these two are set equal, we know that x is going to be maximum when the block leaves the spring, because they're equal. These two forces are equal. So when we solve for x, we will have the distance where the block just leaves the spring. It's just leaving, and at that distance, that would be the maximum stretch of the spring. So let's just solve for that. So x is just going to equal mg sine theta over k, which is equal to 3.2 times 9.8 times the sine of 30 degrees divided by 431 Newton meters, and that's going to equal, and when you solve this equation, you get 0.036 meters.